Hey everybody, how's it going? Welcome to what I believe is the fifth lecture of econometrics for data science. Hey, I'll throw you an extra credit point if one of you emails the first person to email me and tell me what that background is, I'll give you an extra credit point. Pretty lucky to be able to tape this particular lecture from this location. Another thing I want to start off by saying is that today in particular, we're going into some stuff that I think would be good for projects because now we've kind of set up the base for what is the value of econometrics. Focus on modeling, focus on data generating processes, but not necessarily the statistics of data generating processes, but the systems and models that underlie data from theory. So we saw that basically the first day and have mentioned it since. And then we looked at the linear regression basic model last time, going through the assumptions that make that a very powerful model. Today we're going to start thinking about what we do when we violate those assumptions. And this could be a great place to use econometrics because there's going to be many places where you might observe heteroscedasticity. And today we're going to start talking about how we fix those issues when we do linear regression models. So the first thing, so today is called the generalized regression model. And so I'm going to just go over that. It's not probably the least complicated is the fixes to the assumptions. And actually, I'm kind of going to cover autocorrelation too, because the generalized regression model can be used to help us with statistical inference when we are looking at models that might, or data that might be experiencing autocorrelation or heteroscedasticity. So let's start off by just thinking about, I'm going to open our other Colab notebook from last time. So let's go over to our modules and look at our assumptions, because I think there I showed you pretty early on this matrix right here. So this is our variance matrix. A variance covariance matrix, as we discussed, has the variance of the error terms on the diagonal, and then the covariance between different errors on the off diagonal elements. And then this matrix, the spherical disturbances assumption, means that we have constant variance across the diagonal. It's not indexed by anything, indicating that this number, this sigma squared number, is the same on every element on the diagonal of this matrix. And also we have no autocorrelation. So the covariances are zero everywhere off of the diagonal. That is the assumption. That is one of the assumptions that allows us to prove that regression is blue. So the best linear unbiased estimator. Now, when we violate that assumption, we could violate it in one of two ways. First, we could put indices on our sigma squared elements, indicating that sigma squared n, for example, might be a different number than sigma squared 1. We represent that possibility. By now, we are indexing the sigmas, so they might be different numbers. Similarly, on the off diagonals, we no longer have zeros, but we have a row. So row 1, 2 would be the covariance essentially between the first error term and the second error term in our model. Over here, we'd have the covariance between the first error term and the nth error term. We'd expect most models, we expect this to be the small, even if we have autocorrelation, because when these guys are not zeros, that's autocorrelation. When these guys are not the same, that's heteroscedasticity. So in most models, we expect this number to be a lot smaller than this number. So we expect error terms that are for nearby observations, particularly in time series. Because another thing that I'll mention to you down below, and so actually I didn't really need to open that other Colab, I guess, because I have that other matrix right here. So this is our assumption about a model with possibly with heteroscedasticity and autocorrelation. This is our spherical disturbances one. Notice that we can pull the sigma squared out, and then we'd have ones on the diagonal potentially, and then like an omega matrix in here. So this sigma squared is going to be like a common sigma. And so we can talk, there's a lot of different ways to represent this matrix, but in general, recognize the difference between going from here to here and from here to here. This is our basic assumption about spherical disturbances. This is when we bring in autocorrelation and heteroscedasticity. So now we can actually go and reconsider the properties of our ordinary least squares estimator under the presence of heteroscedasticity or autocorrelation. So let's go here. So here we consider the properties of the OLS estimator. Know that the presence of issues might be more likely when working with different types of data. For example, autocorrelation is much more likely to occur with time series data, although we might have spatial autocorrelation and cross-sectional data. So time series data, the variation in our data comes from variation across time, like oil prices are one. So we observe different oil prices on different days, for example. We could also observe different oil prices across space, like different states have different oil prices. If we looked at that, that would be cross-sectional data because space, variation in space or location is what is driving the variation in that data. Autocorrelation is much more likely in time series data. Heteroscedasticity tends to be more likely with cross-sectional data. A really sort of simple example, one that can be easily fixed for heteroscedasticity, if we were looking by like the impact of population on GDP or population density on GDP, we'd likely have bigger error terms in more populated states. We could transform our data into per capita data, and that is often a good fix for heteroscedasticity. So there may be very simple fixes to some of these issues. And we probably should be doing something like per capita, so dividing by population with that type of data anyway. So there are easy fixes to some of these issues if we're critically thinking about how we're displaying or even storing our data in our data sets and what exact versions of different variables we might be using. So let's go ahead and look at the average of the OLS estimator and the generalized regression model. So we have our estimate here, which is x prime x inverse x prime y. And then we can go x prime x inverse x prime, and then this guy. And by pushing, sort of notice that this is x prime x inverse x prime, we can push that through, and then this inverse matrix is going to knock out this x prime x inverse, and that's why we just get this beta alone right here. But then we get this x prime x inverse x prime x on our error terms. And then this is going to go to zero actually under the same assumptions that we had before. So either the average of the error terms is zero or the covariance between x and the error terms is zero. And then that's going to cause this guy to be unbiased. So that's going to cause this to go to zero. So that means our expected value of b is going to be beta. So even under the generalized model that allows for heteroscedasticity and for autocorrelation, we still get an unbiased estimate because the expected value of b will still equal beta under this equivalence right here. Because basically, if we push an expectation through this, this other term over here will go to zero. And then we'll get b expected value b equals beta. So that's a good characteristic. We maintain the unbiasedness of the ordinary least squares estimator under the generalized regression model. Now, the second thing we want to consider is what happens to the variance of our OLS estimator under the generalized regression model. So we have that the expected value of b equals beta. And now we want to know what happens with the variance of b. So we can look at the variance of b, and that's going to be a k by k matrix because it's going to be the variance of the on the diagonal is going to be the variance of b, but then we're going to have covariances between the different b's. That's why it's k by k and not k by 1. So we can take the expected value of b minus beta. So this is just the expected value of the differences between the statistic and the true value, which is just applying the definition of the variance here. And then normally, if we were not doing the matrix version of this, it would just be this guy squared. But since we're doing the matrix version, we do the matrix times its transpose, and that's sort of the equivalent of squaring that quantity. Now we can replace this B minus beta and do some substitutions to get these guys. And then we know that this guy right here is our sigma squared omega from up here. And actually, this is a typo, so I'm going to fix it really quick. There should not be an N, oops, sitting on that. So I'm just going to show you guys what I fixed really quick. This should not have an N sitting on it. The idea is that we could pull out sort of a common variance and then just be left with the uniqueness or the leftover part that makes these variances different. And that's what gives us this sigma squared omega, because the omega matrix is what's left over if that heteroscedasticity on the diagonal. And now we can write the variance this way. And then so we can say B is normally under the assumption that epsilon is normally distributed. B then will be normally distributed with this variance. So now the question, what is this variance relative to x prime x sigma squared I, because that was our variance under the spherical disturbances. So the model that met all of our assumptions. So now our goal is to find an efficient estimator. So we basically can show that yes, indeed, this variance is bigger. I'm not going to prove that for you here. It's a somewhat complicated proof, but it is bigger. We essentially compare this matrix to the matrix that we had before. And so now we want to think about, well, how can we get back to better estimation? Because basically efficient estimation means we want to get to a lower variance. Given that we've discovered we have a higher variance estimate under the generalized model. So our goal is to find an efficient estimator. So the smallest variance estimator among unbiased estimators for our coefficients under the generalized model. So OLS is an efficient estimator under the spherical disturbances, under the assumptions we went across last time. We showed that because it is the smallest variance estimator among unbiased estimators. So, but now that we're given this omega matrix that complicates things, if we know omega is symmetric, which we saw above, because the reason that is the covariance between 1 and 2 is the same as the covariance between 2 and 1. That's why it's symmetric. And then we can pre and post multiply omega by this matrix defined as P right here. And so this is a diagonal matrix with all the eigenvalues of omega along the main diagonal, and C is a matrix of characteristic vectors. So you can, I'm not going to ask you to prove or honestly completely understand what I just said, but if you know about those issues, then you can follow what I'm saying right there. Because right now we're going to design a pretty intuitive estimator right now. So once we get to that definition, we'll talk about it. But this is just the setup that I want you to know how these things come from, because these are really, once you are out in your career, these are the places where if you can understand this, then you can start thinking about and designing these. I mean, that's a very high level thing, but getting there is sort of really, you've got to crunch your brain through these ideas, and having those types of skills will be very valuable in other areas too. So even in places like AI and machine learning, I mean, at the very top levels, you need to be thinking about these issues if you're more than just a practitioner, right? I should say. And so that's why I'd like to show you guys. So again, I'm not going to press you hard on, because this is a pretty complicated thing right here. So then after this definition, we can use matrix algebra to show that the inverse of omega is P prime P. That results essentially from this definition. So we make this matrix to give us this nice characteristic, essentially. And so then we can pre-multiply the population regression equation by this specially defined P matrix, and we get this equation. So all we've done is pre-multiplied our linear regression model by P. And then we can redefine our variables and write this guy this way right here. And then we know that this E star, it happens to be distributed this way. And whoa, What's that? Okay. We've actually discovered that this pre-multiplication gives us back our spherical disturbance matrix. And so essentially, we're just forcing through this pre-multiplication of this matrix to look just like this matrix. So that's fundamentally essentially what's going on here. And so now the classical assumption of OLS are satisfied because we've brought back this assumption through our pre-multiplication by P. And then we have this BGLS estimator where now we have X prime omega inverse X, X prime omega inverse Y. And so, and I believe this should not have a prime at the end of it. Sorry. This should not be prime because it's just like our other estimator, X prime inverse X prime Y. So let's get back there. So sorry about that. Here we go. So I just took off the prime on those Ys. So this looks very similar to our original OLS estimate, but now we have this inverse matrix right here. And you can really kind of think of this inverse matrix now being in the denominator, because essentially what we're doing is we're weighing our observations by the variance and covariance structure of the matrix. Now, if we were doing a very simple model and we weren't thinking about this in matrices, this is would literally look like inverse weighting by variance. So those observations that have relatively low variance of the errors are going to get more weight than those errors that have a high variance. And this is going to allow us, because we essentially, what's driving our high variance result is there's more likely to be weird observations when the variance is high that are going to drive our estimated line away from the true population line. So this model tends to say, hey, put more weight on those low variance ones, the low variance error term observations, because those ones are the ones where you're less likely to get an outlier. So you're less likely to get a bad estimate of B. You're more likely and going to get more efficient estimates on average by seeking out those observations that have lower variance. Now, that's sort of the intuitive. The way I'm talking about it, I'm really focusing on heteroscedasticity. This matrix is also has autocorrelation packed into it because, again, we have this is sort of our omega matrix right here after we pull sigma squared. So clearly there's these rows sitting around. And so this is also taking care of autocorrelation for us. So we can do a little simulation here to compare what's happening on our two estimators. So just looking at what the lines look like, I just estimated a bunch of different lines under random data that I created. And I made sure it had heteroscedasticity by forcing the variance to be different for different observations. And then we see that the blue lines, the OLS lines, are clearly like the slopes of these blue lines clearly have a bigger variance than the slopes of the GLS lines. And then the true line, of course, is this green line. So that sort of visually shows us what's going on. If we sort of average over these red line estimates, we're going to get, honestly, sorry, I shouldn't say that. If we average, we'll probably get similar averages. But if we look at the variance of the slope estimates, those were clearly going to be larger under the blue lines than under the red lines. And now we can look at this omega covariance matrix of the errors, what's going on here. So the way I set it up is that the first observation just has a variance of 1, and then I have the variance increasing down the diagonal. So that just shows that that's happening. And now we have and so this model, my simulation, I didn't do autocorrelation. But then if we look at the omega -1, you can see this is still 1 because that's just 1/1, but now we have 1 over these numbers. So you can think of this is like the weight of the last observation. So that last observation, which has the highest variance, is getting the least weight versus our observations here are also, so our first observation is getting the most weight. One is the highest weight of these, all of these different observations. And then the weight's just decreasing as our variance gets bigger. Okay. So now we can use this to make some estimates. And so this is a specific type of generalized squares. This is called weighted least squares, which is probably the simplest sort of applied thing to do when we're in generalized least squares. And so this is mostly going to deal with inference because this in general will not have an impact on our estimates, although we can. So I'm sorry, I have to be very careful about that. Usually we use weighted least squares for inference. So people are concerned about heteroscedasticity, but because OLS is still unbiased with weighted least squares, they'll go ahead and take the estimate they get from ordinary least squares, but then the variance will be adjusted so that when we're doing hypothesis testing, for example, on that coefficient, we want to be dealing with the correct matrix essentially. And we need that correct matrix if we want P essentially, right? So that's where what the most common, it shouldn't say the most common, the simplest thing to do about violations to spherical disturbances in the form particularly of heteroscedasticity. And so now I decided to plot some natural gas and oil data as we've seen before. And this clearly has some heteroscedasticity going on. So it appears that we have a very high variance right here. And then also sort of higher variance when we have higher oil prices, which is the dependent variable. Now, this is clearly an oversimplified model because I'm just using one variable, oil price, to explain natural gas price. Now, just that mistake alone is probably causing a lot of this heteroscedasticity. But because natural gas prices are so volatile, it's likely that we would have leftover heteroscedasticity anyway. And there's a variety of models that people have applied to that particular problem in energy markets. Often that involves generalized least squares. Often it involves thinking differently about the system, because that's what we do a lot. So thinking about the supply and demand of natural gas, basically, and thinking about what are the things that lead to spiking natural gas prices, cold weather, infrastructure issues, things like that. So there's other modeling ways people try to take care of these issues. But if we were to have just observed this data, we'd want to say, like, clearly we have a heteroscedasticity issue in this data. And then so we essentially just apply our GLS and OLS estimates down here. And you can follow this. You can look at this code to see how we do that. Now, you can iterate these things because it is an iterative process because we always use OLS in our first iteration to figure out things like the variance of the air terms. Now we're not, and then we could do that again. We could say, okay, well, now I have a new B, and then I can do this whole process again and see, okay, what are my errors now that I've done this again, and try to converge to sort of a new, and that's a more complicated thing than weighted least squares, because that's where we're going to start getting into, I actually want, so if we do that process once, as I've done here, then we will sort of, so sorry, I should say this. I'm going to start over the sentence again. You can always do this iteratively because the very first time you are going to use OLS under the generalized model to get your first set of estimates. That's going to give you a set of estimates of Bs, and it's going to give you a set of estimates of your variances. Now we have a new set of, so now we have our first set of error variances that we could work with. Now we could go ahead and weight our observations as described above with these new variances. That weighting if we were not going to stop right there and then we were going to reweight all of our observations, that reweighting will in fact now lead to a new estimate of our coefficients. So it's depending there. That's why. So for inference, we can basically say, I'm going to accept my coefficient from OLS. But then for statistical inference, like hypothesis testing, I do need to pay attention to the fact that I have weird variance, because that's going to feed directly into statistical inference. If I just look at my OLS standard errors, that's going to be too small, essentially, of a standard error. However, if I don't stop there, I take my OLS coefficients and then I say, okay, now I have some variances. This is like my first estimate of the variance covariance matrix. So this is kind of like my first estimate of omega. We saw above that the generalized least squares model, we can weight with those new things on our omega matrix. That will actually allow us to do new coefficients. Those new coefficients, and now those are generalized least square coefficients. Those new coefficients are going to change our line and change the errors in our variance covariance matrix. So that's like a new estimate of our variance covariance matrix. And we might reweight again at that point. And we could keep doing that. And we could sort of check how much are our coefficients and our covariance variance matrix changing on each iteration. And then we could just stop when we get to a level that's acceptable to us. So that's sort of going on in the background when we use the stats model GLS package. And we can code that by hand. And sometimes you have to, because there's often options with how we want to deal with the generalized regression model. And your options are going to be somewhat limited under what's other people have built in stats models. So we don't necessarily need to always use stats models. We could hard code this. I don't think I do that with heteroscedasticity, but I will do that with some more complicated, like when we get more into endogeneity, and you'll see how we can just hard code estimates. And essentially it amounts to defining X prime, X prime, X inverse, defining all those matrices, and then using Python to do the matrix calculations, or sorry, the matrix operations, because we know the matrix operations. B equals X prime, X inverse, X prime, Y is a matrix operation. Python can handle those. So we can just, instead of using these packages, explicitly get our estimates using that math. And so I want to just show you the results of this process now. So when we do, here's our GLS regression results. And we see that on our constant term, we have 0.34, and on our oil price, we have 0.035. And then our standard error here is 0.001. So a pretty tight fit. And that is statistically significant right there. And it's interesting. This is a pretty narrow confidence interval. If we go down here and we look at the OLS results, first of all, we do have slightly different results, because in this version in stats model, it is doing the iterative process and applying that to our coefficient estimates. And then we see, so that's why this number, the GLS one, is not the same as this estimate. And then we also see that this is a much wider confidence interval that's driven by the bigger standard error right here. And that's essentially because at the very beginning, we showed theoretically and said, we're going to have and experience larger standard errors from this. And it's not necessarily like, you want to be careful here, because observing this number being different than this number is not really evidence of biasness, because this is one sample. This is really more evidence that those high variance results or those high variance observations in this sample, something about those are making our line too shallow and not steep enough. And then when we do our weighting, then we're going to get a more, because probably the weighting is leading these to get very low weight, some of these guys to get very low weight, but the line is likely upward sloping in here. So it's possible that the variance is actually bigger down here as the lines going through here. Yeah, these ones are going to have low weight, but we do have some low variance sort of looking observations in that region as well. So apparently, those guys were making our line look a little bit too shallow. And then when we applied GLS, we got a steeper line. So that's essentially what the differences in results will look like under GLS. Sorry, this is probably good timing for that, and maybe a clue for your extra credit point that I told you about at the beginning of the video. But anyway, it was nice to see you guys here today. I know this is getting a little bit more complicated, and even my talking about it, it'll get a little wishy-washy because it's much more complicated. Please don't hesitate to reach out to me if you have any questions about this. I tried to wet the palate for this a little bit by having you guys do a heteroscedasticity sort of exercise in the last homework. But yeah, I will see you next time. And don't hesitate if you have questions. Thinking about this for projects could be great because you can probably think about different data sets that are going to experience the issues of autocorrelation and heteroscedasticity. Bringing those ideas to me would be great sooner than later. And even if it doesn't have to do with this, a few students have already brought ideas to me. So yeah, just let me know if anything is floating around and we will discuss it. All right. I will see you guys on the flip side.